Jai Hind to all. My name is Divya Sharma and today's video lecture is on horizontal vertical antennas and Yagi-Uda antenna. So first we will discuss horizontal antenna, then vertical antennas, then Yagi-Uda antenna. First we will start with this horizontal antenna. Now what do you mean by this horizontal antennas? So horizontal antennas above a plain ground. It means what? Field pattern is much affected by the reflection from the ground. The reason is that ground is considered as reflecting surface. Now here for the horizontal antenna, horizontally lambda by 2 antenna at the height h above the plain ground of infinite extent. So we will show in the figure when the antenna is grounded or ungrounded but the close to the earth is directional characteristics field at distant point P are changed. The radiation directed towards the earth is reflected. Thus the total field in any direction will be vector sum of the direct and reflected radiation from the ground. For the purpose of this analysis, it is convenient to regard to the reflected radiation coming from the image. It means what? You are considering here horizontal lambda by 2 antenna and you are considering that you have an antenna and you are finding the mirror image also. So this is your antenna, horizontal antenna of length lambda by 2 and this is the height from the ground, h. Now here you are taking the mirror image of this horizontal antenna. So mirror image of this antenna, horizontal antenna is same, height means same for the mirror image, that is also same h, and horizontal length of this horizontal antenna lambda by 2. So it means what? This is the mirror image of this horizontal antenna. If you are considering here, it means you have two cases, direct wave or reflected wave, right? So let us consider this is your horizontal antenna, height of this horizontal antenna is h and this is the mirror image point of this antenna, same height h. Now here you are seeing that this is the direct wave of angle theta and this wave, when this wave is coming, it is reflected back. So this is your reflected wave from the ground and your angle is, this is your phase reversal angle and you have a point P. Now here you are considering point P, right? So and this is your antenna, this is your point P, and when you are sending wave, so your wave is in direct wave or you have reflected wave. Now in order to obtain the field at a distant point P, it means we are applying the method of images as discussed in the previous slide. We are considering the following points. First point is that resultant field is made up of direct and reflected wave. So mirror image being the virtual source of the reflected wave. Now second is ground is assumed to be perfectly conducting so that the tangential component of the electric field must vanish at the surface. Therefore the reflected wave must suffer a phase change of 180 degree. It means your angle is phase shifted by 180 degree. So this condition is satisfied by taking the current image equal to magnitude but reverse in phase by 180 degree to the antenna current. Now the third point is that the shape of the vertical pattern changes while the horizontal pattern remain the same. So these are the following points when have to consider when you are considering a antenna and a distant point P for the horizontal case. Now ground affected horizontal antenna. So let us consider this is a point, this is your A dash. You have this horizontal antenna. So this is point A, this is point A dash for the horizontal antenna of length L. So this is the length for this horizontal antenna and located at the height h from the ground. And in this figure B dash is the mirror image. So here this is the horizontal antenna and this is the mirror image of this antenna A dash. So it is mirror image is considered as B dash. Now when you are considering the horizontal antenna, your phase is first 90 degree then minus 90 degree. But when you are means first positive, this is your magnitude positive, here your magnitude is negative. But if you are taking the mirror image, so height is same, this length of this antenna is also same L, but phase is changes by 180 degree. So here your magnitude is positive, here your magnitude is negative. Now in the original horizontal antenna, if your magnitude is negative here, so in the mirror image your magnitude is positive here. So there is a change of phase shift of 180 degree. So this is horizontal antenna. Now field calculation for grounded affected horizontal antenna, it means you are considering this antenna A and this is your point P. So this is your horizontal antenna, means this is the center of the horizontal antenna. This is point P. So you can consider here this is the distance R. Now here angle, when you are drawing this point P, so angle by this point P to the horizontal, to the axis, that is represented by theta. If you are considering vertical case, vertical, this is your vertical line, so angle from this point to this vertical line, vertical axis, that is represented by phi, and this is the height of the antenna. Now if you are considering the mirror image, the height is same, angle phi, this is your angle phi, and now here you are considering this distance, so you can find out this is your 90 degree, this is your phi angle, so you can find out this distance according to your Pythagoras theorem. You can find out that is equal to 2h cos phi. So this is the field calculation for grounded affected horizontal antenna. Now here already it was discussed in the previous slide that it is 180 degree out of phase. Now here, if the path difference between the radiation from A to B will be 2h cos phi, or the phase difference equal to 2 pi upon lambda and into 2h cos phi. So for the let a phase difference between radiation from two antennas due to opposite current, that is equal to beta. So you have to write down the total phase difference. Total phase difference is equal to alpha is equal to beta plus 2 pi by lambda in bracket 2h cos phi. So this is your total phase difference. And now here you can see EA represents the field at point P due to this antenna AA dash, and EB is what? EB is due to the antenna, that is your mirror image of the horizontal antenna, is representing by BB dash. So total field at point P is equal to what? EP is equal to under root EA square plus EB square plus 2EA EB cos, in bracket this is your theta angle. Let us consider beta plus, means you have to put this angle, total phase difference, beta plus 2 pi upon lambda 2h cos phi. So here EA is equal to EB, as already discussed in the previous slide, that downside you have a mirror image of the original horizontal antenna. So you can put here EA is equal to EB. So while putting this value EA is equal to EB, you will get this equation. This is your resultant field at point P. EP is equal to, so you can take common EA, 2 in under root 2 plus 2 cos theta beta plus 2 pi by lambda 2h cos phi. Now here you can take common under root 2. You will get this equation 1 plus cos 2 in bracket beta by 2 plus 2 pi h upon lambda cos phi. Now from this equation you can write down 1 plus cos 2 theta is equal to what? 2 cos square theta, right? So you can write down 1 plus cos theta is equal to cos square theta. You can put here the value 2 cos square. This is your theta. Theta is your beta by 2 plus 2 pi h upon lambda cos phi. Now here from this equation you can take common under root 2. So you will get here 2 EA cos, this is your theta. Theta is equal to what? Beta by 2 plus 2 pi h upon lambda cos phi. Now here beta is equal to what? Beta is equal to 120 degree. So total field at point P is equal to 2A cos theta. You can put here the value beta 180 degree, then you will get here 90 degree plus 2 pi h upon lambda cos phi. Now here 2 is equal to what? This you can find out, you can put here the value of 90 degree. You will get this equation minus 2 EA sin 2 pi h upon lambda cos phi. So this is your total field at point P. Now you can solve it. You are getting here cos phi. So you can solve it. Cos phi is equal to what? Cos 90 degree minus theta, and cos 90 degree minus theta is equal to sin theta, right? So your equation, finally your equation is EP is equal to minus 2 EA sin 2 pi h upon lambda sin theta. So this is your, the field is proportional to what? Field is proportional to 2 sin in bracket 2 pi h upon lambda sin theta. So this is your total field at point P. Now polar diagrams for this previous equation, it means the various values of h by lambda. So here you can see the radiation pattern, means polar diagram for when you have height above the ground, lambda by 4. So this is your polar diagram. Now height above the ground lambda by 2. So this is your radiation pattern. Height above ground, that is equal to what? 3 lambda by 4. So this is the radiation pattern. If you have height above lambda, so this is the radiation pattern. Now height above ground 2 lambda. So this is your radiation pattern. And here height above ground 4 lambda. So this is the radiation pattern. It means what? It means there are various radiation patterns when you have different height, like lambda by 2, lambda by 4 to 4 lambda. Now next antenna is vertical antenna above a plain ground. Now you are considering here vertical antenna and this is your axis. It means what? This is your ground. Now here height of this vertical antenna is represented by L and this is the point P, means two distant points. This is your point P and you have to consider from this axis. So radius of this point P to this axis means ground. Your radius distance is represented by R and angle drawn by this line means by this point is represented by theta. Now again you have to take mirror image of this vertical antenna. So length is same for this image antenna, that is represented by L. Now again you have to find out the power at point P, right? So calculate the field at point P due to this vertical antenna and you have this vertical antenna represented by A and A dash. Here image of this vertical antenna is represented by B and B dash. And now here you can find out this distance from this axis to when you are considering the center of this vertical antenna. So you can find out this distance. This is equal to what? 2L cos phi. So you can put here this value. You can take here this is 90 degree. This is the angle phi and you can find out according to the Pythagoras theorem. You can find out this distance is 2L cos phi. Now here total phase difference is alpha is equal to 2 pi upon lambda and this is your path difference. Path difference is already calculated here. Path difference is what? Because you are considering this point and you are considering this point. So your distance from this point to this point and this point to this point is R. But you are considering from this mirror image, center of this mirror image. So you have to find out this extra distance also. So this is equal to what? 2L cos phi. So this is the path difference, or you can say this is path difference. So put here the path difference 2L cos phi, and since beta is equal to 0, you have alpha is equal to 2 pi by lambda 2L cos phi. Now you have to find out total field at point P due to this vertical antenna. E is equal to what? Under root E is A square plus EB square plus 2EA EB cos in bracket 2 pi by lambda 2L cos phi. Now here EA is equal to EB. So EA you can take common, under root 2 also you can take common and you will get this equation 1 plus cos 4 pi L upon lambda cos phi. EA is equal to EB because you have taken here EA. When you are put EA is equal to EB, so here put EA. Here also you can put EA, you can take common under root 2 EA. So you will get this equation. Now here again 1 plus cos theta is equal to what? 2 cos square theta. So you can take, you can put here 2 cos square theta and you can take common under root 2 again. You will get here 2 EA cos. Here you have under root. So cos square theta, it means you will get here cos theta. So cos theta is equal to 2 pi L upon lambda cos phi. Now here you have cos theta means cos 2 pi L upon lambda cos phi. So you can write down in this form. In sin theta, that is E is equal to 2A cos 2 pi L upon lambda sin theta. So this is in term of cos and this is in term of sin. Now radiation pattern of some antennas due to this vertical antenna means you have to find out radiation, you have to draw the radiation resistance when you have antenna length lambda by 8. So this is the radiation resistance. So this is the radiation pattern for antenna length lambda by 8 and this is the radiation pattern for lambda by 4, lambda by 2, then 5 lambda by 8, 3 lambda by 4 lambda. And this is the radiation, sorry, this is the antenna height, means this is the antenna height lambda by 8, lambda by 4, lambda by 2 and this is the radiation pattern for this and this is the radiation pattern for this. Okay, so this is your radiation length. This is your antenna length, this is antenna length, this is antenna length, this is the radiation pattern for this, this is the radiation pattern for this, this is the radiation pattern for lambda by 2, Now here when you have height lambda 5 lambda by 8, so this is the radiation due to 5 lambda by 8. This is the radiation pattern for due to 3 lambda by 4. This is the radiation pattern due to you have antenna height lambda. Now the third one is Yagi-Uda antenna. Yagi-Uda antenna is most commonly used type of antenna for TV reception over the last few decades. It is most popular and easy to use type of antenna which have better performance, and it has high gain and directivity, and its range is operated in the range of 30 megahertz to 3 gigahertz, which belong to very high frequency and ultra high frequency bands. So there are three types of element within a Yagi-Uda antenna. First one is driven element, second is reflector, and the third one is director. So first is driven element. The driven element is the Yagi antenna element to which the power is applied. It is normally a half wave dipole, or you can say folded dipole. And reflector, it means what? Reflector, the Yagi antenna will generally only have one reflector. This is behind the main directive element, that is the side away from the direction of the maximum sensitivity. For the reflectors behind the first one and little to the performance. Now director is what? Director, or you can say directors, are placed in front of the driven element, that is in the direction of the maximum sensitivity. It means each director will add around 1 dB of gain in the forward direction, although this level reduces as the number of directors increases. So these are the three elements of this Yagi-Uda antenna. Now we will see the structure of Yagi-Uda antenna where we can see the driven element, reflector and director. So this is the structure of dipole antenna with directors and reflector. So here this is the driven element, this is reflector, this is the back side, these are your directors. So this is the stand. Now driven element, you can see these are your directors, this is the reflector. So this is the structure of this Yagi-Uda antenna. Now the basic element used in Yagi-Uda is half wave dipole, which is placed horizontally, known as driven element or active element. In order to make the unidirectional, additional rod elements are placed on either side of the dipole antenna. So these elements have no electrical connection with the dipole. So these are known as parasitic elements. And the elements longer than the dipole are placed behind, it is known as reflector. And elements having length less than the driven element, and it is placed in the front of the driven dipole, that is known as directors. And directors is always directed towards transmitting antenna. So these are the silent features of Yagi-Uda antenna. First is driven element is usually a folded dipole which is excited. The director is a straight conductor placed in front of the driven element towards the transmitter, and reflector is a straight conductor placed behind the driven element. Now second is director and reflector are also known as parasitic elements. The length of the folded, third one is the length of the folded dipole is about lambda by 2, and it is at resonance. It is at resonance. Now fourth point is the length of the director is less than lambda by 2. Now the fifth point is length of the reflector is greater than lambda by 2. Next point is radiation pattern is always unidirectional. And next is the effect of parasitic elements depend on their distance and tuning. So, and the last point is last feature of Yagi-Uda antenna, the purpose of the reflector and directors is to increase the gain, but they load the driven element. So these are the silent features of Yagi-Uda antenna. Thank you.